Hello. In this video, we will be talking about critical values and the critical value method. Let's first see what critical values are. And if you recall, we talked about critical values while we constructed confidence intervals for mean and proportion. The critical values separate the critical region from the non-critical region. The symbol for critical values is CV, critical value, or value. A critical region or a rejection region is formed of the range of values of the test value that indicates that there is a significant difference and that the null hypothesis should be rejected. The non-critical regions or non-rejection region is the range of values of the test value that indicates that the difference was probably due to chance, and then the null hypothesis should not be rejected. This is how we will actually make the decision using what is called the critical value method. Whenever we use the critical values in the critical values method, we need to sketch the graph. I have an example right here for a z-test. As you can see, we are using right here the z-distribution, but we can do the exact same thing when we use the t-distribution. We learn in this class how to perform hypothesis tests using z distributions or t distributions. Again, this example is for the standard normal distribution. But the same way, the whole theory applies when we use the t distribution. So for example, if we are doing a left tail test for the mean, the hypothesis will look like this. And we will use the critical values to divide the area under the curve into two regions. So if it's a left tail test, the critical value will actually separate the critical region, and this will be the region far to the left from the non-critical region. So this is how we will actually find the critical values. We will have a negative value right here. It's only one value. This is the critical value. Now, something else, and you may see this notation here, the area in the tail, it's actually alpha. So we know the area in the tail. This is where the critical value is, and this is actually alpha, area in here. To find the critical value, when we know the area, you can find the negative ZC by doing inverse norm. Area to the left, which is alpha, 0, and 1. This is how we found values when we use the z-distribution. When we use the t-distribution, we are actually doing inverse t, and we want to make sure we put in the degrees of freedom after we put in the area. Now, if we're talking about the right tail test, the whole idea of what we've done moves to the right tail. You will be ending with a positive critical value. Critical region will be far from the mean, so it is in the tail. The area right here is actually alpha. To find this value, you simply do inverse norm, and this time area to the left, which is 1 minus alpha, 0 and 1. Of course, if we are doing a z-test. Now, for a two-tailed test, this is what happens, and you should be familiar with this because we actually done that when we constructed confidence intervals for the mean and for proportions. So right here, we will have two critical values, one negative, one positive, and alpha will actually be split in two. So right here, we have an area which is alpha over 2. So right here, you see the two critical values, the notations, right? If the test statistic falls in a critical region, we will reject the null hypothesis. So as I was saying, the basic rejection rule while using the critical value method is reject H sub 0 if the test value or the test statistic falls in the rejection region. For a right tail test, this happens if the test statistic is greater than the critical value, which is denoted Z subscript alpha. For a left tail test, this will happen if Z is less than Z alpha, And for a two-tailed test, reject H sub 0 if it's in a critical region, meaning greater than Z alpha over 2 or less than negative Z alpha over 2. Now, if we are discussing this and instead of Z, we are using the T distribution, then the notation will change accordingly. Reject H sub 0 for a right-tailed test if T is greater than T alpha, which is the critical value, or for a left-tailed test if T is less than T alpha, and for a two-tailed test if T is greater than T alpha over 2, or T is less than negative T alpha over 2. However, I would strongly suggest to sketch the graph, shade the area, and it's as simple as plotting the test value or the test statistic on the graph and see where it falls instead of remembering this, but whatever it's easier. So I'll just write down here if T distribution is used. Now, the critical value method was actually the first method used in statistics in doing hypothesis tests. And at that time, the technology was not advancing so fast. We were using tables. And this is actually called the traditional method. Since then, we have the calculator, we have so many softwares available for us. So we are using now the p-value method. This is commonly used a lot more than the critical value method. However, there is value in learning this method too, and that's why we're talking about it right now. Let's do this problem using the critical value method. A doctor working at a busy city hospital is interested in studying the ages of patients who visit the hospital. He claims that the mean age of patients who arrive at the emergency room is greater than 46 years old. A sample of 40 patients had a mean age of 49 with a standard deviation of 10 years. Use level of significance 5%. So let's write down the given information and see what type of test we will be doing. He claims that the mean age, so this is a test for the mean, is greater than 46. And then, let me just write down, this is the claim. And then he takes a sample of 40 patients that will be sample size, and he finds the mean age of those, that will be an X bar, which is 49 years old, and the standard deviation, it says with a standard deviation, so this is the information from the sample, so that will be an S, which is 10 years. And the question is, do a test for this claim. I will also write down that alpha is 0.05, it says right there. So it's a test for the mean. Let's proceed. So I'll write down the steps as we know it, and I'll tell you when I will change it to adapt to the critical value method. Here is the first step. The first step stays the same. We should always write down the null hypothesis and the alternative hypothesis. So I will say, here is my claim, which means that is the alternative hypothesis, and this is the claim. And we already know that this will give the direction of the test. So this is the right-tailed test. And now the null hypothesis will be less than or equal to 46. Okay, so I have my first step done. Step 2, I will have to decide what test do I use. So first I start with the distribution. I look through the given information and I realize that S is given, not sigma. Because of that, I'll be using the T distribution, which means I can use the formula to find the test value or the test statistic. However, I will be using the t-test to get the test value. This time I'm interested only on the test value or the test statistic. And I write down alpha here, which is the level of significance. And now at step 3, I will come up with the critical values. This is the difference. So right here, find the critical values, and then from the test, find the test statistic or the test value. So critical values and then test value or the test statistic. For the test statistic, we do the test on the calculator or we plug in the formula, but we will do it on the calculator. But how do we find the critical values? This is how we find the critical values. Sketch the graph. This is a T distribution. And I should write down here what is the degrees of freedom. Degrees of freedom is 39. We all know that, right? So this is one curve from the family of curves, n minus 1, right? N, which is 40 minus 1, 39. Now, this is a right tail test. So right here, I'll have my right tail. And here is what you will need to know. The area in the tail is alpha. So right here, this is 0.05, which means to find this critical value, which is the T, I can call it T alpha or TC critical value, okay? To find this value, I'll be using inverse T area to the left, which in this case, it will be 1 minus 0.05, which is 0.95, and the degrees of freedom, 39. And if we do this with the calculator, we get 1.68. It's positive, and we know it should be positive, right? So this is the critical value. Right here, I'll just write down TC is 1.68. So keep that in mind. This is directly related to the area in the right tail, because this is the right tail test. The area in the right tail is alpha. So we've done all of this work to get to the critical value. And now I will plug in the t-test to find the test statistic or the test value. Now, if you've done this correctly, plug in the information, you should have this value, which is t, and this is all we need from the calculator for using the critical value method. I know the P is right there, and we can go right away and conclude this using the p-value method. But keep in mind, we are learning now how to use the critical value method. So the only information is this one. This is the test statistic, which in this case, it's 1.89 or 90 if I round to 2 decimal places, okay? So what I will do next, I will take these values and put it right here. The critical value is right here, which is 1.68, okay? This critical value is actually dividing this area under the curve into two parts. One to the right, which is called the rejection region, and the other one to the left, which is called non-rejection or non-critical. And we simply have to take this test statistic and place it in one of these regions. How do we place that? Here it is. It's 1.90. I'm looking at where 1.90 will be compared to what's right here on the t-axis. Well, it seems that 1.90 it's greater than 1.64, right? So this is the t, which is greater than tc. It falls in a rejection region. So I will say now at step 4, reject h sub 0 because the test value or the test statistic falls in a rejection region. Or you can simply say because t, this was t, the test statistic, is greater than tc. And that means it falls in a rejection region. That's how we conclude the test. So see, this is critical. You want to make sure you will sketch the graph. You will place the critical value first, separate the regions into rejection and non-rejection regions, and then take the test value that will be found by using the calculator, okay? Place that value in one of the two regions. Of course, you have to just follow the rule. You are in the on the number line, moving from left to right. So 1.90 will fall to the right of 1.68. And now that we are done with this, we know we reject the null hypothesis. Step 5, we will interpret, and I will say at alpha equals 0.05 level of significance, there is or is not enough evidence to support or reject the claim that the age of patients who arrive at the emergency room is greater than 46 years old. So now you can stop the video and try to plug this in, then check later. Or keep in mind, we rejected the null hypothesis, which means we always start with is. Right here, there is enough evidence to support or reject the claim. Well, the claim was the second one, the alternative hypothesis, and it seems that we are supporting that. And this concludes the critical value method applied to this problem. Okay? So before I end the video, I want to just show you the difference between critical value method and the p-value method. Basically, we have to follow a certain number of steps, but if we want to do this problem actually using the p-value method, we will not need the critical value. So this is the part that you will have to do some work for, because this is not displayed right here under the test. But you will do the test. You will not need to do this using the critical values, but you may want to do this for the p-value, right? And from the screen, after you do the t-test, you will look at the p-value. The p-value is 0.0326. So write down the p-value here. You may want to sketch a graph too, but this time the graph, it's actually relating the test statistic, which is 1.90 right here, and the p-value, which is 0.0326. These two are related this way. One is the area under the curve, the other one is the number on the axis. Okay, while with the critical values, the area was alpha, and the corresponding value on the t-axis is called the critical value. So we see that actually we reach the same conclusion. We say reject H sub 0, but we will have a different reason. We will simply say, well, we reject H sub 0 because the p-value is less than alpha. This is the reason if we're doing this using the p-value method. And the final conclusion is the same. Okay, so all you need now is practice. And with this, we conclude the video. Thank you for watching.